So this is section 813 for my BC children on arc length, and it is the last section in Unit 8 before we go on to Unit 9. And it's kind of interesting. It's how do you find the length of a curvy thing? That's really what the arc length is talking about. So it's not a straight line distance. It's more of a curvy thing. So the idea behind finding arc length is very similar to the way that we find area using calculus. We're going to divide the curve into a large quantity of small segments and find their lengths and then add them up. So recall the regular old distance formula from back in the day. Gosh, when on earth did you learn this? Had to be a long time ago. Big old square root x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Kind of based off the Pythagorean theorem. We can approximate the length of a graph of a function f by using n line segments whose endpoints are partitioned between a and b. Think of it this way, that a is x0, your initial x value, and b is where you're finishing the final x value. And you're taking little segments between that where you start, the initial value, and where you stop. That's the math gobbledygook idea of it. Let me show you a visual. It makes it a little bit easier. Say this piece here is A, and this piece here is B. I'm going between A and B. And I want to know the distance between these 2 points. This distance. Now that's going to give me some answer, but how accurate will that be for the distance of this red curved part that goes between those 2 points? And you can tell it's going to be a lot smaller than what the actual length of that is. So let me change up my colors and try this. What if I were to pick a point, I don't know, let's say pick a point right about here. And if I were to find the distance between that, I'm going to call this first guy D1. D sub 1. It's my first distance. My second distance is going to go this way. So this would be, I guess I shouldn't have used red because it's hard to tell where the curve is. Let me highlight the curve. See if this helps. All right, here's my curve. And now I've got, this is distance 2, and this is distance 2. If I were to add them up, would that be closer to the actual value of the curved distance? And it would certainly be closer than my D1, right? So then I think about, well, geez, what if I were to make it even smaller? What if I were to go every 2, like, this is a width of 2. This is going to be my D3, and then it goes from there down to the curve. This is D3, and then I'm going to go 2 more. That's going to put me here. This is D3, and then I'm going to take my last one that goes this way, and this is my last D3 to connect all those pieces. Am I getting more accurate as I go? And of course the answer is yeah. The more segments that I make, the more accurate it's going to be to the actual length of the arc, of the curve. And so that's what they're trying to say here. The more line segments I can make, the more accurate my answer is going to be and closer it's going to be to the actual length of that curve. So the arc length, that's what the definition is, and that's what the concept is. So there's a couple of things you have to consider. It has to be a continuous curve. Can't have any gaps in it or jumps or any of those types of things like a piecewise function type deal. So it must be continuous. And we said the more segments that you take, the more accurate your answer will be. So, lovely mathematicians came up with a really cool formula to make life easy for us. The more segments you take, the more accurate your answer. Okay, that's good enough. You got the idea. And here's what they said. If I take the integral, remember integrals are like the infinite number of rectangles, or in our case, an infinite number of segments going from A to B of the square root of 1 plus, and then you want your derivative of the function squared with respect to x. That, my friends, is going to give you, oop, you can't see me, that's going to give you the value of that arc length. And so there's the formula. The integral from A to B of the square root of 1 plus whatever the derivative is squared. And so they say, all right, well then find the arc length of this guy. So we're going to put it in the formula. I want to go from 1 to 4. So I'm going to take the integral from 1 to 4 of the square root. All right, now think of the derivative. Maybe off to the side here we might want to put what the derivative is. The power comes down in front, so now I've got 1/12 times 3 halves. And I have to take my group, x squared plus 8, to 1 less power. 3 halves minus 1 is 1/2. Don't forget the chain rule, because then I need to multiply it by the derivative of what's inside, 2x. And that's going to be what I get. So let's see if we can clean this up before we put it into our integral. I have 3 times 2 is 6. So I have 6 over 24, or 1/4, x. And then I have my group, x squared plus 8 to the 1/2 power. All right, so then I'm going to put it in here. So I've got 1 plus, right, my 1 plus. My derivative, 1/4 x, x squared plus 8 to the 1/2 power. But I got to square it. And guess what? That's the piece that most people forget when they're putting the formula together. They tend to forget that you've got to square that inside part. Well, there's a lot of different forms. That's a perfectly valid form, but there are a lot of different forms you could see. This is more like a multiple choice kind of question on an AP exam, and there's other equivalent forms that it could look like. So let me show you some of them. One of them would be the integral from 1 to 4. This is probably the one that I would leave it at. I would simplify it to this place. 1 plus x squared. Now remember, you're taking 1/4. You're going to make that 1/16. X squared. And then if I square this square root, it gets rid of the root. So now I've got x squared plus 8. So you see I just squared all the pieces because they're all being multiplied together. So I can just square each piece. That would be one equivalent form. Here's some others that I saw given on the curriculum video. They did this. They did 1/16 on the outside. Actually, inside your square root. 1/16 plus. And then they put 16. Isn't this bizarre? 16 plus x squared. Parentheses x squared plus 8 with respect to x. So in other words, they changed it and factored out as the 1/16 out of the whole thing, which is kind of odd, but that's what they did. And then they also put it as, I guess I should put all these as equals because they're all the same thing. Here's another one that I saw. It is the integral from 1 to 4 of 1/4, and then the square root. They took out that 1/16, and it was x to the 4th plus 8x squared plus 16 with respect to x. So you can see there's so many different ways you could write this. So again, you're going to get your answer, and then you're going to check out the multiple choice choices and see which one is most likely to line up with it. But just FYI that there's a lot of different ways that you could write it. All right, next one. We've got Often a problem will only ask you to set up the integral. We saw that in the last couple sections where they were doing that. But we could take it further and use a calculator. So set up an integral that represents the length of a curve, y equals sine of x between 0 and pi, and use a calculator to evaluate it. All right, so what we're going to do, one thing you want to make sure any trig functions involved, that we are in the radian mode. So check your calculator out for that. And I usually use a capital L to talk about arc length, meaning length, of course. And I'm writing the integral from 0 to pi. They're my bounds. And I think of, if I have y equals the sine of x, I need the derivative. Well, the derivative of sine is cosine of x. So here I go, plug it in. 1 plus the cosine of x squared with respect to x. And so I'm going to go to the calculator. Let me pull out my calculator here. And whatever method you like best for finding an integral, I'm going to go with, let's go with the y equals. I tend to like that the best. So, I want to check my mode. I am in radians, so that's good. Y equals. I prefer to put this in as 1 plus, and then I'm going to put parentheses, the cosine of x, close that, raise it to the second power, another parenthesis, and raise that to the 0.5 power, the square root, the 1/2 power. And I like the y equals, again, I've told you this before, because I can see that my input is corrected. Is it put in really the way that I wanted? And yeah, that looks good. So I'm going to graph it. Kind of looks a little straight line-ish with a little squiggle in there. I don't know. And then I want to know, F5, what the integral is, 7, going between 0, my lower limit, and pi. Pi is second caret. And so the guys inside the calculator tell me, hang on, I'm busy. There it is, 3.82. 8202, let's be more specific. All right, that's it. So you can do it on the calculator as well. Same way we find integrals for anything else. So you can do that through the home menu. You can do it through that graphing way as well. And then they give a proof of how it is that they came up with this from the distance formula all the way down into our formula for what the arc length actually is. Now, all of these, interestingly enough, they give you this the squiggly equals. And the squiggly equals just means that it's an approximation. So you're looking at what it's approximately, because, I mean, how many segments are you taking? You're taking an infinite number of segments and adding them up to get to that arc length. So it's going to be an approximation, not an exact value. And that's it. That's the whole lesson. So let's pick and choose some of these that that we might want to look at. Let's try number 2. All right, so number 2. Put myself down here. I thought this one was kind of interesting. It took a little doing to get there, and it makes sense once you think about it, but the length of a curve from x equals 1 to x equals 3 is given by, okay, if the point 1, 6 is on the curve, which of the following could be an equation for the curve? So in other words, if this is what the arc length looks like, what's the equation of the curve? And so we know that this, 4x squared, represents, remember the formula is 1 plus the derivative squared? We know that this represents y prime squared, 4x squared. Or, if I take the square root of both sides, right, y prime would be 2x. Now, that's what the derivative is. The question's asking, what would the original curve be? Well, the original curve is a y equals. How do you go from a y prime to a y equals? You integrate. And so if I integrate, this 2x becomes x squared. Remember, you take one more power, divide by the power, so the 2's cancel. And then you've got some value of c. could be, it's a parabola of some sort, but it could be up or down from wherever that might be. So we have enough information to figure out what C is because they told me X and Y. Y is 6, X is 1, and I can see that C is going to be 5. So therefore my equation would be X squared plus 5. Yay, that's one of my choices. So kind of interesting. They're taking you a little bit backwards on that in order to be able to solve that. Let's try number 5 as our next one. Number 5. Here it is. This one is thanks to Joey. When I first did the answer key for this, I kept getting the problem wrong and I couldn't figure out what I was doing wrong. But after a discussion in class, Joey helped me out and I realized where my mistake was. So thank you, Joe. This one's a calculator question. Consider the region bounded by the graphs of y equals f of x equals x squared minus 4 and g of x is 5. Write an expression using one or more integrals that could be used to represent the perimeter of the region. Kind of interesting. I'm going to go up here just above and I'm going to take a picture of this. All right, so I've got 1, 2, 3, 4. I have Mr. Happy parabola, x squared minus 4. And then this is the line of y equals 5. Right here. Along this guy, going out that way. So what we want to know is actually let me use this guy. What is this perimeter? Well, part of it's going to be an arc length, right? Because it's a curve. Part of it is going to be going from this coordinate all the way around to this coordinate on the curvy part. And part of it is just a straight across. So I've got to think about this for a second here. Where do they equal? Where do they connect? Where do they intersect, right? We've seen this before. If I take x squared minus 4, I want to know where it intersects with 5. And so I'm going to set up my equation. I'm going to solve for x. And I know that these coordinates here are the coordinates negative 3, 5 and positive 3, 5. Which is then going to help me to figure this out. So write an expression using one or more integrals that could be used to find the perimeter of this region. And then part B is find the perimeter. So really, ultimately, that's where I'm going with this. So let's set up our integral. It's going to be the integral going from, let's do the curvy part first, negative 3 to 3 of the square root of 1 plus. Well, the curved part is the parabola. The parabola, let me come over here, y equals x squared minus 4. If I take its derivative, I get 2x. And so I'm going to put that into here, 2x squared. So that would be the integral that would show that. And then what I need to do is add on the rest of this straight part. Well, how big is the straight part? It's perfectly horizontal, so I can just take from negative 3 to positive 3. How far is that? And that would be a distance of 6. And so really that's the expression that's going to get me the whole situation here. So I'm going to go to the calculator. For the sake of time, I'm going to let you put that in there. But if I put this into the calculator, this part comes out to be 19.494. And then I'm going to add my 6 onto it, and my final answer for the perimeter is 25.494. Most of the times these are calculator questions. Although I think number 4 is done without a calculator, so be careful with number 4. Number 4 is not one of those. All right, let's see which next one I want to do. Let's try 10. Might be another one that's a little bit more challenging. Word problems, we love them, yeah? All right, calculator active, Mr. number 10. a trajectory, can you say that? Trajectory of a ball thrown from a height of 150 meters is given by the equation, yada yada, until it hits the water, where y is the height of the ball above the water and x is the horizontal distance traveled in meters. Find the distance traveled by the ball from the time it's thrown until it hits the water. So if you think about it, it kind of looks like this. You throw the ball in the air and then it comes down and it hits the water. Water, here's the ball. Okay, so you want to know what that curve would be. Find the distance. So here's what you got to think about. You know it starts at a time of 0, right? Your initial time. So what I'm trying to do is set up my integral. My initial time is 0, but I don't know right now when it actually hits the water. So I have to figure that out. It's going to hit the water when my value here equals 0, right? Because it has no height at all. So it's going to be 0 equals 160 minus x squared over 40. And I want to know when that happens. So let's see, there's a couple things that we can do. I'm going to move the x squared over 40 to the other side to keep it positive. Gotta love positives. And then I'm going to solve this out. It ends up that x equals 80. That's what my upper bound is. That's when it hits the water. So that might have been a part of this problem that might have thrown you a little bit for a loop. You got to think that through a little bit. All right, now let's go with the rest of this. 1 plus, well, what's the derivative? I don't know, let's go over here. Y prime. Derivative of 160 is 0. So now I'm taking the derivative of negative, I'm going to put write it this way, 1 over 40 x squared. Right, that's what this term would be. So 2 comes down in front. Now I've got negative 1 over 20. And then I have 1 less power, so an x. So here I am in here, negative 1 over 20 x quantity squared. There it is. And so I go to my handy dandy calculator and I figure out what that value is. It's a calculator active question. Plug it in and out pops from your friends inside the calculator 185.871. All right, I'm going to choose one last one, 13, and then we're going to call it a day. We have number 13. This one's kind of big on the page, so I'm going to probably have to, maybe I can make my zoom a little less. It doesn't let me do that when I'm in the middle of recording. Okay, anyway, we'll make it work. So this one I thought was kind of interesting because, again, it's a mountain hike consists of a steady incline followed by a curved hill and then a flat valley. Here's the formulas that go with it. The mountain hike is modeled by a piecewise function defined by f above, and the graph of f is shown in the figure. Which of the following expressions gives the total length of the hike from 0 to 9? So I want to know what it's doing from 0 to 9. They do this often where they don't make you figure out the whole, like they're not including 10. You notice how that's off the grid. You're only going to 9, even though the graph goes to 10. So be very careful of that. Make sure that you're with what they're talking about. And it says that it's modeled by, from 0 to 4, a straight line. This is a straight line, right? Y equals mx plus b. So if I'm thinking of that, that's not part of a curve. I don't need the L formula because the L formula is for curves. So I'm going to put on here from 0 to 4, just to here. And if I think about this, check this out. I want to know what this length is right here. I'm going to put a big question mark there. I don't know what that length is. But I sure enough know that this is a right triangle, and I know that this side is 4 and this side is 3. And you should be doing a little happy dance because we automatically know what this missing side is. It's a Pythagorean triple, a 3, 4, 5 triangle. So my big old question mark is really a 5. And then I'm going to go to the the curve part. You see the curve part? The curve part's going from 4 to 8. There's my curve part. So far I have a 5 plus the integral from 4 to 8 of 1 plus. Now, of my 3 formulas, the only one I care about is the middle guy right now. I've already taken care of this first one. He gave me a value of 5. Now I'm on to the middle guy, the curvy guy. And the curvy guy kind of makes sense because see how it's a squared function? So that is a squared kind of parabola-ish thing. And so I'm looking at this and I'm going to say, all right, well, I need to know what the derivative of that is. So if I figure out the derivative, there is no derivative. It's 0 for 5. The 2 comes down times 1/4 gives me a negative 1/2. I take my group to 1 less power. That's to the first power now. And I take the derivative of what's inside, which is just a 1. So there it is. That's what I'm putting in here. I have a negative 1/2. I have an x minus 6. And that whole thing is being squared with respect to x. And then I have this. I'm looking at my answer key is different than what I'm looking at here. I've got this should be just a value of 1. All right, so I've got plus a 1, but we're going to come back to that in a second. So since it's stopping at 9, was going 0 to 9. Okay, so this should just be a value of 1 for this piece. This one was a 5. You'll see the dilemma in a second. We'll talk about it. All right, if I were to then calculate this out, this middle, well, you don't even have to. I have 2 plus, well, definitely not 2 plus, it should be 6 plus. This is an integral growing from 0 to 8, so this one's off already. This one is going 2 plus the integral from 0 to 8. This one is still like not even in my ballpark. This one, 7 plus 4 to 8 of the integral of 1 plus, I don't even know where they're coming up with all this craziness. So this is not even part of our dilemma either. The last guy fits, right? The last guy, if I square this, then it's a positive 1/4. It's an x minus 6 quantity squared, so I got that. This one is the 1, but here's the dilemma. It's 7 plus rather than 6 plus. And here's what I think the problem is. I think that they meant for this to go from x equals 0 to x equals 10, so that you're including this extra 1, so now you have the 7. Do you see what I'm talking about there? I know I was talking in Babylon without you seeing the answers at the bottom. But the answer that fits is the 7, I'm going to put on the extra plus 1, plus this integral that's then been squared. So D is the correct answer. There's a bit of a typo in the midst of that. It should be going from x equals 0 to x equals 10 in order to fit their multiple choice answers. The way that they have it written, you would have it as 6 plus the integral from 4 to 8 of the square root of 1 plus 1/4 x minus 6 quantity squared dx. And that's it. That's section 813. So not so bad. Kind of a nice little formula to follow. And it's going to come up again later when we talk about parametric and polar equations. So hang on to that. Keep that in your wheelhouse. And I will see you in class. See ya.